Hi, this is Roger from Kanka Labs, and this will be a companion video to our first Kickstarter campaign promoting this power-inductor checker. The reason why I publish this video before is, one reason is it shall be a kind of appetizer before the campaign starts in 2 or 3 weeks, and on the other side it might be also of interest to my subscribers because, as you already can spot perhaps, the circuit is completely open source, so the schematics and the PCB layout and the BOM, the bill of materials, will be freely available online. And now in this video I will explain first of all what is it good for, what do you need additionally to what you see, what can you measure with it, and how does it work, how is the circuitry built up. Now, as you perhaps also can read, the idea was for this measurement device was inspired by elmchang.org. He devised the idea how such a power-inductor checker could be built up, and so all respect goes to him. I've made a few changes to the circuitry just to adapt it more to a commercially producible unit. So anyway, as you can see, it is for measuring inductors. The reason is a modern multimeter, it can measure in today's world not only resistors and capacitors as passive components, but when it comes to measuring inductors, I don't know of any multimeter which can do that. So you either have to buy an expensive LCR meter, and then you have a further limitation. An LCR meter can only measure the amount of inductance of your inductor, but it cannot measure up to which current your inductor is working. So the purpose of this device is twofold. First of all, you can measure the inductance of unknown inductors, and a second is you can measure at which current the material, here as a ferrite material on a toroidal inductor, when it goes into saturation, which means up to which maximum current can you use it. And what you need additionally to the power-inductor checker is, as you can see, you need a power supply between 3 and 16 volts. The current capability is not so important, so any lab supply with 1 amps or more current capability is enough. And as you can see from the BNC connectors, you need an oscilloscope just to display what happens when you use this device. So let's start from left to right, what you have to connect and how it works and what are all the components for. By the way, this is our prototype model. As you can see here, we still had originally provisioned for an internal 9-volt battery, but we have decided it's not necessary. The reason was to give the 2 555 timers used here and the power MOSFET here to give them a minimum voltage between 5 and 9 volts to operate correctly. But we have seen, as you can see here, the whole device operates with external power from between 3 to 16 volts safely, and I will later explain why it's better to go to the upper range of the voltage. Best is to use anything between 9 and 12 volt. The maximum of 16 volt is first of all due to the maximum operating voltage of the 555 timers and the used capacitor bank here. So if we connect our power supply, first of all it's still turned off. We have 2 little diodes, and the first one, the green one, starts to light up something around 4 volts. So you perhaps can see it now is quite dimly lit up, but it becomes brighter when we go to a higher voltage. And at the maximum allowed voltage, the red, or here in the prototype it's still orange, the orange or red LED turns on so that you can see now you're in over voltage and you should reduce the voltage. So when you see the green LED lit up, you know your supply voltage is in the right range. So then you see a large capacitor banks out of 10 electrolytics with each with 1000 microfarads. So all in all we have 10 millifarads, and we need this power bank because we will for very short time spans we put the supply voltage to your inductor, and we can measure currents up to 60 amps. So, and even the ohmic losses in the cables are much too large, so we need an onboard kind of power tank just to keep the voltage constant for very short times, even when we go to currents through the inductor of dozens of amps. All in all, we can measure up to 60 amps, so that's quite astonishing for such a small device where you cannot see any power resistors or something like that. So I will explain that later. So after the two LEDs, we have our first 555 or 555 timer. This generates just a constant pulses in the range of 50 Hertz. That's just for the repetition rate, so that on your oscilloscope the measurement repeats every 20 milliseconds, so that you get a clean triggering and a clear picture with enough repetition, with a high enough repetition rate. But the core of the circuitry is the second 555 timer. And as you can see, we have a little slide switch where we can change to 3 different ranges of the time span that we put the voltage onto our inductor. So from 1 microsecond, when you put the slide switch in the upper position, and the potentiometer, where you get a fine control. By the way, it's a logarithmic potentiometer, so that you can even the span of from 1 to 50 microseconds is a ratio of 1 to 50, so you can finely control it with the logarithmic potentiometer. And the lower range, the third range, goes up to 20 milliseconds. That is the maximum because the repetition rate is just 50 Hertz, so 20 milliseconds measurement time, or time where we put voltage onto our inductor, is the maximum. So the combination of the slide switch and the potentiometer, thereby you determine the range, how long the voltage is put onto your inductor. And then you can see a power MOSFET here with extremely low on resistance, and it's a special type, not only with extremely low on resistance, but also which also switches at safely into the milliohms range with only a few volts of gate voltage. And then we have here a Kelvin resistor, so a 4 contact resistor of 10 milliohms. That is our shunt resistor with 4 terminals, just to measure precisely the current through the inductor. So it lies in series with the power MOSFET. And then we originally had 2 BNC outputs. The first one is the basic measurement output. That is just the voltage developed here over the shunt resistor, which is a direct measure of your current. And the second one we provided for a trigger output. But we have seen, no matter if you use an analog or a digital scope, you don't need the external trigger output. So in the finally sold version, we will probably leave the second one out or unpopulated, you still can use the connections down below. But I think it's just enough to have the basic output, because we had stable triggering with any oscilloscope that we tried. So now let's think a moment to get an idea of what happens when we put through the switching of the MOSFET, when we put the supply voltage here from our capacitor bank to an inductor. What happens is the current through the inductor will rise linearly with time. And many people understand very well how capacitors work, but have a problem in changing their view when it comes to inductors. Now it's quite easy. You only have to interchange voltage and current, and a capacitor and inductor behave the same way if you just interchange current and voltage. Now let's think for a moment, what happens if we put a constant current to a capacitor? Well, there the voltage will rise linearly. And the other way around, when we do not put a constant current but a constant voltage to an inductor, then the current will rise linearly. Well, linearly, but only up to the point where saturation sets in. And that is the one of the two purposes. We can measure the inductance just by the slope of the linear curve we will just in a minute see on the oscilloscope. So the slope in conjunction with the amount of the supply voltage, that gives you directly the inductance of your inductor. But we will see that the slope at some point starts to not be linearly anymore, but will develop into a curve. And there are two reasons for this. The first is you have always the copper resistance. So the linear rise of the current cannot go on up to infinity. Finally, there is the ohmic resistance, which limits the maximum current just to ohms, just according to Ohm's law. And the second is, except for coils wound on air. Air coils are linearly 100%, but whenever you use, just like in a transformer, you have special transformer sheet ions, even in toroidal transformers, or in this power inductor here, you have special ferrite materials. And there is always a point when these ferromagnetic materials get into saturation, so the current will not rise anymore, and your inductor will even start to get warm if you would put the maximum current for an extended period of time. So this cannot happen here, because we only let the current rise either up to the time that you set here, or even if you set it the wrong way, or there is a kind of hardware fuse inside, because when the voltage developed here over the shunt resistor, when it becomes 0.6 volts, then a transistor turns on. You can see it here, a small SMD resistor, and this resistor will shut off the 555 timer. So the current can never become larger than 60 amps, because that's the limit for the shunt resistor as well as for the MOSFET. So you have an extra protection. Nothing can happen, neither to your inductor, simply because the time is very short where we let the current rise. So even if we go into full saturation, you will not be able to destroy your inductor with the circuit, and on the other way, the circuit cannot be destroyed by overcurrents. So that was quite a clever idea how Elmchang made up this circuits, and as I told you, we made a few modifications. And now let's take a look at, you can already see I've put, what I forgot. Here we have provided professional binding posts, so you can either directly clamp your unknown inductor, and that's the best way to directly clamp it here to the binding posts. Because of course, when we are dealing with tens of amps, every milliohm of contact resistance counts, and you should have the shortest and lowest, the shortest possible connection with the lowest ohmic resistance. But you can also, of course, take 5mm banana cables with, for example, crocodile clips or whatever, and connect it distantly to your unknown inductor. If the current does not exceed a few amps, then the resistance of your cables and the contact resistance will be low enough that your measurement result will not be too much out of the correct as what it should be. So now let's go over to the oscilloscope and measure. So let's start with our first example. Here I've put a known inductor, or inductor with known properties, into the binding posts. It is rated with 100 microhenries at 5, goes up to 5 amps without any losses or without any saturation effects. So let's start with our first example. I've set the supply voltage to exactly 10 volts because then we can easily or more easily calculate the values from the displayed graphics or from the oscilloscope curve. Now, first of all, I will show you some tricks what you can do with the digital storage oscilloscopes. First of all, if we set the oscilloscope to vector mode, you will see that at the beginning and at the end of the measurement cycle there's a little spike. That's due to parasitic capacities charging or discharging, and this spike is quite helpful for triggering, because that way we really don't need the trigger out BNC terminal, because no matter if you use an analog or digital oscilloscope, it will easily trigger onto this first spike. And let's put it back to dot mode. So now the two spikes nearly vanish and they don't disturb us anymore in the measurement. Second is, the nice feature of digital oscilloscopes is that you can put the y-axis, the scaling of the y-axis directly into amps. That's when we put here at the unit current, we do not choose the regular voltage as the displayed unit, but we choose amps and as the probe factor, because we have a factor due to our 4-terminal current sense resistor. We have 100 amps per volt, perhaps you can read it here, so we have a 100 times probe, and thereby we immediately get the right units displayed. As you can see now, we have 500 milliamps per division as the y-axis scaling, so we can easily now read off the values of time and current. So we don't have to do any math in our head or with a calculator. We can directly read the values off from the oscilloscope screen. That's of course not possible with an analog oscilloscope, but I think that many of you already have a digital storage oscilloscope. So next is, I put the origin on the lower left corner, so that we can use the full screen. And now we start for every inductor in the lowest setting of the slide switch, which gives us a variable time between 1 and 50 microseconds. And I will turn it back for a minute. So if we increase now the measurement time, or the time that the inductor is switched to our capacitor bank, then you will see that except for a little wiggle in the beginning, which is due to inaccuracies of the circuit, so don't worry about that. These wiggles are not due to the inductor, they are due to parasitic properties of our components. So anyway, if we increase it from the lowest value, we're now at around 700 milliamps, and increase it up, the curve is very linear. Now we have reached 4 division, which gives us 2 amps, so we are nearly at half the rated current of this inductor, and we're still seeing a very straight line. And now we will reach the end. This is the end of our first setting, of the lowest setting of the timing switch here, of the slide switch. Now anyway, we're not at the rated current, but we can first of all make our first measurement, and what is quite helpful is the cursor function of our digital oscilloscope. So we switch on the cursor to track mode, and I've only selected one out of 2 possible cursors. And now we take one point of our on the upper point of our graph, of our quite linear graph, and we measure here at this point we have 53.4 microseconds and a current of 2.3 amps. Now we could go with this value already into our formula, but there is still an easier way. Here on the measurement values, you can set the rate of, which is nothing else but the slope of our linear graph here. So the only thing we now have to do is we have to divide our supply voltage through the, we have to divide it by the rise rate, the slope of our curve, which is given as jumping around a bit 63 kiloamps per second. And now I'll try to make it in a way that you hopefully can read the numbers. So we divide 10 volts supply voltage by 63K, or 63,000 amps per second, and the result, let's put it into units, gives us 158.7 microhenry. Here you can see the 10 to the minus 6. So at this point we have an inductance that is higher than the nominal inductance of the coil. So the question is, what is wrong, or is this something on purpose? And we will later see when we increase the current that this inductor has in fact 160, round it, 160 microhenries at currents below the maximum rated current. So that's quite an interesting result. When we are below the rated voltage of a power inductor, then we can expect that it has a larger inductance than the nominal inductance that is given by the data sheet. So now let's switch to our, let's first of all do our timing potentiometer to the minimum value and go to the middle position of our timing slide switch and increase now the time and thereby the current more. And now you can see the the curve does not behave linear anymore. Here is around the point where it starts to slope upwards. We're at 2.24 amps. That's around half of the rated amps. And now we will change the scale of our oscilloscope 1 to 1 amps per division. And when we now go up, you can see that now it becomes quite unlinear here, and we will now go exactly to the rated current with our cursor. Sorry if my arm always is in the way. So let's tweak around a bit, and here we are at exactly, more or less exactly 5 amps. And now the rate, the total slope here has changed a little bit to jumping around a bit to around 90 kiloamps per second. And this is the slope measured from the initial point 0 microseconds and 0 amps up to 5 amps. And if we put that into our calculator, we get 10 volts divided by around 90 kiloamps per. And what do we now get? We get 111 henries. So that is regarding the 10% tolerance of the inductor, and that to be really exact, we would have to measure the slope here between two narrow points. So not from the beginning to this point, but just let's take one division as measurement. You can do all of that with the cursors. You can use dual cursors and take the difference between time and amps. So you can do a lot of measurement here simply directly with the oscilloscope, even without using a calculator. All of that will be explained in detail in the forthcoming manual. And now let's still further increase the current, and we have to turn back the y-axis now to 2 amps per division, and you can see I would now even have to take the time base also. I would have to change it, but you can see the curve starts to slope upwards faster and faster, and that means that the inductance of our inductor becomes smaller and smaller the higher the current becomes. And we also can see that the point of saturation does not start at the rated current of 5 amps, but it starts much lower at around half of the rated current. So let's turn it back again. Let's try to determine the point where the inductor becomes unlinear, and there is around here this point, and we are at 2.9 amps. So you cannot exactly determine the point where saturation sets in, but this is about half of the nominal current, and there already saturation effects come into play. And at the rated current of 5 amps, this inductor is already quite unlinear and already, well, perhaps not heavily into saturation, but saturation effects in the ferrite material. You can perhaps see there's this toroidal inductor is wound on a toroidal ferrite core with a yellow color. The saturation effects come into play already here at consistently lower currents than the rated current. And if you use this inductor at 5 amps, it will already start to heat due to the losses inside the ferrite material, which are in the end an effect of the saturation or unlinearity here, or the unlinearity is an effect of saturation. So this shall be enough for our first example. So you can see that with one measurement you can determine two things. First of all, the point where the saturation sets in, and secondly, by a simple formula, the amount of inductance at different points of the curves. As long as it's linear, the inductance is constant, but when the curve starts to rise, the inductance becomes smaller and smaller, and you could determine the inductance for every point of the curve, either with the cursors directly on the scope, and the math function, and or you just measure 2 points and put the 2 points into the formula. So as a second example, I've put a toroidal mains transformer here to the input terminals. This one here is rated with 2 amps for the secondary winding, and transformers, no matter if they are of the standard type, the more rectangular type, or such toroidal transformers, the magnetic material that is used inside is most often some kind of special iron sheets, here wound spirally for a toroidal shape. It could also be some special kind of ferrite material, but most often these are special transformer iron sheets. And these are well known for being very unlinear, so you cannot expect, if we increase the current and thereby the magnetic field in the toroidal transformer, that we get a linear response. But how unlinear, that we will see. We are already here. We have now set the Y scale to 200 milliamps per division, and I will now slowly start to increase the current, and you can see until now it looks still quite linear, but now here at around 200 milliamps the curve is shaping upwards and becoming very unlinear, and we're not nearly at the rated current of 2 amps. Now we have 8 divisions. Of course we can use our cursor just to find the exact amount. We're now at 1.5 amps, and if this transformer is rated for 2 amps RMS, the peak current will be 2.8 amps. So now I've set the cursor to exactly 2.8 amps, and you can see when we have the maximum current flowing through the secondary winding, we're at a very unlinear point, which already looks like saturation, but transformer materials are just designed for working in the nonlinear part of the curve. We could also look upon it as that the material, that transformer iron, is the core of the transformer, made out of special transformer iron, is just designed to work here without too much losses in the, well, it's in the unlinear part, but at this point is the kind of design point for this transformer, and this does not mean that there are too many losses. So a nonlinear curve does not necessarily mean that we have excessive losses here. the really linear part only goes to around 200 milliamps. It's just the design point, and of course we could now measure again the inductance here at the design point, but that's not very interesting for transformers. That is more interesting for inductors where you really have to have a fixed and known inductance. So this will be it for the two examples, just to demonstrate what you can do with this little power inductor checker in combination not only with a digital storage oscilloscopes, but also of course with analog scopes. You just have to take the readings here with an analog scope directly from the screen. And here you can just use the cursor function just to ease your measurement. So let's go on now to some math, the math behind, or the theory behind inductors. So let's finally take a look at the math behind measuring inductors with this method. There is a basic definition, the voltage U. Please excuse me if I use the letter U instead of V, as you might be accustomed to in the US. In the rest of the world, just to discern voltage from volts, the letter U is used for a voltage. So the voltage that develops over an inductor is the inductance in itself times the change of current dI divided by the time the current is flowing. So this gives, that means when we have a constant voltage and the inductance is constant, then we get also a constant. This dI over dt must be also a constant, and that means it looks just like this. When we look upon the time the current related to time, we will get a linear rise, and the slope itself is a measure for the inductance, because when we know our voltage and we measure here the current and the time at whatever point we have on our graph on the oscilloscope, then we can put it directly into the formula and get out the inductance. If we change the equation to give you L, the inductance, we just have the voltage divided by dI over dt, and we can also, if this is linear, we can just say, well, we've measured one point I, the current, at one time t, then we can also write this as U, the voltage, times the time of the measurement point divided by the current. That's how easy it is. We know the voltage, the supply voltage that we put onto our power inductor checker, and we read off the time and the current from our oscilloscopes. Of course, because we measure with our oscilloscope the voltage developed over the shunt, we still have to convert the measured voltage into current, and that is simply the measured voltage divided by 10 milliohms, which is 0.01 ohms. That gives us the current. And with modern oscilloscopes, as you can see with modern digital oscilloscope, you even can set the scale directly at your oscilloscope, so you can read off from the y-axis from your oscilloscope with a modern digital oscilloscope directly the current, and you don't have to use Ohm's law just to calculate it. So that's how easy it is. We know our supply voltage. We measure at one point of the linear curve the time and the current, put it here into this easy formula, and we get our true inductance L before saturation sets in. And now you might have, as perhaps I did, wondered why when saturation sets in the current goes into this direction and why it doesn't taper off here that way. Now that is simply when the inductance due to saturation becomes smaller, then the current will rise faster and finally it will taper off due to the ohmic resistance to a maximum value. So that means the higher the slope you see on your oscilloscope, the smaller your inductance is. So that is basically all you have to know. Just measure off at one point current and time on your oscilloscope. You know your supply voltage and you can calculate the inductance of any known or unknown inductor and compare it with the nominal value if you know the nominal value. Or in another way, if you have an unknown inductor, you can just calculate the inductance plus the point where saturation effects set in. So that was it for a introduction and basically all you have to know about the power inductor, its limitations and its uses. And thanks for watching. And if you watched this video before our Kickstarter campaign started, then, well, there are still a few weeks to wait, but you can already build one of your own because it are, except perhaps for the power MOSFET and the Kelvin shunt resistor, the 4-terminal shunt resistor, everything else are standard components. So you can play around with this circuit already at home. And if you liked it, you can join our Kickstarter campaign. So thanks for watching. Until next time, bye from Roger, bye from Kanka Labs.